Welcome back to The Explainer. Today we're diving straight into the modern machine learning toolkit. We'll be starting our journey looking at how algorithms handle incredibly complex, messy data, and we're going to travel all the way to the totally mind-bending frontier of zero-data solutions. If you want a structured, clear understanding of how the most advanced models actually think and solve problems, you are in exactly the right place.
So here's the fundamental challenge, right? What exactly do we do when our standard run-of-the-mill linear models completely fail to capture the real world? Because let's face it, the real world doesn't operate in straight lines. Real data is curved, it's anomalous, and it's severely lacking in neat little labels. When basic regressions and simple groupings fall apart, we have to open up an entirely different set of tools.
All right, here is our roadmap for today. We've got 5 main stops. First, going beyond basic machine learning. Second, the power of ensembles. Third, decoding sequential data. Fourth, learning with limited data. And finally, the zero-shot frontier. Let's get into it. Starting off with Section 1, Beyond Basic Machine Learning, where we're tackling shape and structure.
Take a look at this. This is kernel regression, and it's a perfect example of breaking out of the rigid mold. Instead of learning a strict set of parameters like a standard polynomial regression would, this is non-parametric. It relies entirely on the data itself. Notice how tweaking the hyperparameter b completely changes the shape of the regression line? On the left, it's a nice, smooth fit. But crank it up, and on the right, it's highly sensitive, strong overfitting, basically hugging every single data point by relying on the actual distance between them.
Now, what happens if you only know what normal looks like? Say you're trying to detect a secure network intrusion, but you have practically 0 examples of what an actual attack looks like. Well, enter one-class classification. We basically draw a boundary entirely around our one normal class, modeling it as a multivariate normal distribution. Think of it like a massive multidimensional bell curve. This curve maximizes the likelihood of our normal examples, so anything that falls outside of it, boom, instantly flagged as an anomaly.
But hey, sometimes the complexity isn't about the shape of the data, it's about the labels. What if an image is simultaneously a photo and a portrait? That's a multi-label headache. But there's this absolutely genius trick where we can combine correlated categories into what's called a fake class matrix. So we map photo and portrait into fake class 1. Painting and portrait become fake class 4. Suddenly, we've transformed this tangled multi-label mess into a totally standard multi-class problem. The best part? It keeps our labels correlated so the algorithm won't make impossible predictions. It's a lifesaver, honestly.
Moving on to Section 2, the power of ensembles, or as I like to call it, the wisdom of crowds. All right, so when we talk about ensembles, we're really looking at 2 main heavyweight paradigms, bagging and boosting. And the difference in their approach is absolutely crucial. In bagging, which is what gives us the famous random forest algorithm, we build a bunch of shallow, low-accuracy decision trees in parallel. Every tree gets a random sample of the training data, and by averaging their predictions all out, we massively reduce variance and avoid overfitting. Boosting, though? Totally different beast. It's sequential. Algorithms like gradient boosting build trees one after the other, specifically designed to fix the mistakes of the previous trees. To put it simply, bagging reduces variance, while boosting reduces bias.
Let's actually step through that gradient boosting loop to see how it works under the hood. Step 1, we start with a basic constant model. Step 2, we compute the residuals. Now, residuals is just a fancy word for the errors, the exact difference between our prediction and the true target. Step 3 is where the real magic happens. We train the new decision tree not on the original labels, but strictly on those errors. Then, step 4, we add this new tree to our existing ensemble, dialing it in with a learning rate. We just repeat this over and over, continually fixing errors until we're left with this incredibly powerful, super accurate metamodel. Okay, Section 3, decoding sequential data, bringing in the dimension of time.
So far, we've talked about static stuff, but what if your model needs to translate an entire sentence over time? You can't just classify that all at once. For this, we need sequence-to-sequence learning, or seek-to-seek. It uses this really elegant 2-part architecture. First up is the encoder network. Its job is to read the incoming sequential input and compress it into a state, basically a numerical embedding of its underlying meaning. Then, part 2 is the decoder. It grabs that numerical meaning and generates a completely new sequence of outputs, step by agonizing step.
Here's what that looks like in practice. The encoder, those are the blue boxes you see here, processes the English phrase, "the weather is fine," going time step by time step until it hits a final state. Then, it hands that single final state over to the decoder, the purple boxes on the right. The decoder unpacks that single state to generate the French translation, il fait beau, one word at a time, using whatever it just output as its very next input.
But wait, what if the sentence is a paragraph long? That single final state becomes a massive bottleneck. You just can't cram all that meaning into one state. Enter the attention mechanism, those yellow nodes right there. With attention, the decoder doesn't just stare at the final state. It actually gets to access the state vectors from all previous encoder time steps. This is a total game changer. It brilliantly solves the problem of retaining long-term dependencies, letting the network literally pay attention to the specific parts of the input sentence that are most relevant to the word it's translating right now.
Which brings us to Section 4, Learning with Limited Data, the Scarcity Frontier.
Okay, what do we do when labeled data is just impossibly expensive to get? Say you only have a tiny budget to pay medical experts to label some data. You definitely can't ask them to label everything. Our first trick here is active learning. It basically calculates a score for your unlabeled data based on two things, density and uncertainty. It specifically hunts down data points that sit in dense, highly representative areas of the dataset, but where the model is currently super confused, maybe sitting right on a decision boundary. The algorithm essentially raises its hand and selectively asks the human expert to only annotate those specific, highly informative examples. It squeezes the absolute maximum value out of every single label.
Another wildly powerful approach is using an autoencoder. Think of this like an hourglass. The goal is to reconstruct the input, but we intentionally force that data to squeeze through a tiny bottleneck layer right in the middle. We intentionally corrupt the input with noise and force the network to denoise and rebuild it using maybe only 10 bottleneck units. By making it struggle like that, we trick the network into learning the deep, fundamental representations of the data, and we do it with barely any labels at all.
Now what if you literally only have a handful of images? Like setting up Face Unlock on your phone. You can't train a traditional model on one selfie. For this, we use one-shot learning with a Siamese neural network, and we train it using something called a triplet loss function. It sounds complicated, but here's how it works. You take 3 images, an anchor image of you, a positive image, which is a different photo of you, and a negative image, which is someone else entirely. The triplet loss function mathematically forces the network to shove the anchor and positive embeddings closer together while simultaneously pushing the negative image far away. It's not learning raw classification anymore, it's learning the literal distance and similarity between things. And finally, we arrive at Section 5, the zero-shot frontier. This is where things get truly mind-bending. How on earth do we predict labels without any training data for that label at all? Well, zero-shot learning works by mapping abstract features within word embeddings. Imagine a word embedding where the dimensions represent abstract concepts like animalness or yellowness. If the model learns what animalness looks like from horses and dogs, and it learns what yellowness looks like from lemons and the sun, it can theoretically classify a picture of a yellow bird, or even guess what a unicorn is, just by combining those known abstract concepts. It is literally identifying objects it has entirely never seen in its training data.
And wow, that brings us to the end of our explainer today. We've traveled from bending regression lines to fit messy, chaotic data, all the way to algorithms that can piece together abstract concepts to identify the completely unknown. It really leaves us with a provocative question, doesn't it? If our algorithms can actively learn to identify things they have practically never seen, what are the true limits of what machines will eventually be able to understand? Think about that next time you're working with these tools. Thanks so much for joining me, and keep learning.